You have already learned that the equilibrium in a system having two or more phases is known as heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. The concentration of these solids or liquids remains constant and does not change. Hence, while writing the equilibrium expressions for heterogeneous equilibria involving a pure liquid or a pure solid, the concentrations of these substances are excluded. Consider the thermal decomposition of calcium carbonate in a closed vessel. Solid calcium carbonate decomposes on heating into solid calcium oxide and gaseous carbon dioxide. The equilibrium constant for this reaction can be written as Kc is equal to the product of the concentrations of calcium oxide and carbon dioxide divided by concentration of calcium carbonate. Since calcium carbonate and calcium oxide are solids, their concentrations remain constant, and hence their concentration terms in the expression for equilibrium constant can be ignored. Now, the modified equilibrium constant for the system becomes Kc' is equal to concentration of carbon dioxide, or Kp is equal to pressure of carbon dioxide. This expression clearly shows that at a particular temperature, irrespective of the masses of the two solids, calcium oxide and calcium carbonate, there is a constant concentration or pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate. It has been found experimentally that the pressure of carbon dioxide in equilibrium with calcium oxide and calcium carbonate at 1073 Kelvin is equal to 2.5 into 10 raised to the power 4 Pascal. Hence, the equilibrium constant at 1073 Kelvin, which is equal to the pressure of carbon dioxide, is equal to 2.5 into 10 raised to the power 4 Pascal. Some characteristics of equilibrium constant are: the value of equilibrium constant is independent of the initial concentrations of the reactants and products. For example, the equilibrium constant for the reversible reaction of gaseous hydrogen and gaseous iodine in a sealed reaction vessel, irrespective of the initial concentrations at 731 Kelvin, is 46.4. The equilibrium constant for a particular reaction at a particular temperature is always constant and changes only with a change in temperature. For example, the equilibrium constant for the reaction of 1 mole of gaseous nitrogen and 3 moles of hydrogen combining reversibly to form 2 moles of gaseous ammonia at 298 Kelvin is 6.8 into 10 raised to the power 5. At 400 Kelvin, it is 41. And at 500 Kelvin, it is 3.6 into 10 raised to the power minus 2. The equilibrium constants of a forward reaction and its backward reaction are reciprocals of each other. For example, the equilibrium constant for the reversible reaction of gaseous hydrogen and gaseous iodine to form gaseous hydrogen iodide at 731 Kelvin is 46.4. The equilibrium constant for the reverse reaction of the decomposition of hydrogen iodide at the same temperature is the inverse of the equilibrium constant for the forward reaction of the formation of hydrogen iodide from hydrogen and iodine. This is equal to 1 by 46.4. If a chemical equation is multiplied by a certain factor, then its equilibrium constant must be raised to a power equal to that factor in order to obtain the equilibrium constant for the new reaction. For example, the reaction of nitric oxide and oxygen to form nitrogen dioxide may be written in two equivalent ways. The first way of writing it is 1 mole of gaseous nitric oxide and half a mole of gaseous oxygen combining reversibly to form 1 mole of gaseous nitrogen dioxide. The second way of writing it is 2 moles of gaseous nitric oxide and 1 mole of gaseous oxygen combining reversibly to form 2 moles of gaseous nitrogen dioxide. The equilibrium constant for the reaction of 1 mole of gaseous nitric oxide and half a mole of gaseous oxygen combining reversibly to form 1 mole of gaseous nitric oxide may be written as Kp is equal to concentration of nitrogen dioxide divided by the product of the concentrations of nitric oxide and oxygen raised to the power of half is equal to, say, X. The equilibrium constant for the reaction of 2 moles of gaseous nitric oxide and 1 mole of gaseous oxygen combining reversibly to form 2 moles of gaseous nitrogen dioxide may be written as Kp' is equal to concentration of nitrogen dioxide raised to the power of 2 divided by the product of the concentrations of nitric oxide raised to the power of 2 and concentration of oxygen is equal to Kp square, which is equal to X square. Thus, you can say that the equilibrium constant for the second reaction Kp' is equal to the square of the equilibrium constant of the first reaction.